All right, welcome everyone. Today, we're going to go on a bit of a journey. We're going to dive into what a lot of people see as this behemoth C++ code base, the guts of PyTorch. And I'm going to hand you a map. My whole goal here is to make the magic behind this framework not just understandable, but actually feel kind of simple. So let's get into it. Everything really kicks off with this one single question. If you use PyTorch, you're using tensors all day, every day. But what is actually happening under the hood that makes them so ridiculously fast and so incredibly flexible for machine learning? How does it do that? Well, to answer that, we've got to start right at the heart of PyTorch, and that is the tensor itself. It's the building block for everything we do. But to really get a feel for its power, we need to pop the hood and take a look inside. So we're probably all familiar with the basic stuff, right? A tensor has a size, it has a dtype, is it a float or an int, and it has a device, telling us if it's living on the CPU or on a GPU. But there is one more piece of the puzzle, one bit of metadata that most people never think about, and it is the absolute secret ingredient to PyTorch's power, strides. Okay, so here's the crucial idea you need to grasp. There's a big difference between how we think about a tensor and how the computer stores it. To us, it's this nice, neat, multi-dimensional grid. That's the logical view. But in reality, it's just one long, flat, continuous block of data in memory. That's its physical reality. So how on earth does PyTorch connect those two worlds? And that brings us to the big reveal, the secret of strides. Strides are the magic map. They are the instructions that tell PyTorch exactly how to jump around that single, flat block of memory to create the illusion of our multi-dimensional grid. Let's make this super simple. Imagine we have a basic 2x3 tensor. This is the logical view. This is what we see in our code. 2 rows, 3 columns. Looks pretty straightforward, right? But here's what the computer actually sees. It's not a grid at all. It's just a one-dimensional, boring, flat line of numbers. The whole concept of rows and columns has just vanished. So how in the world do we find an element, like the one at row 1, column 0? This is where strides do their thing. A stride just tells you how many steps you need to take in that flat memory block to get to the next element in a specific dimension. So to find our element, we start at the beginning, we multiply the row index, 1, by the row stride, multiply the column index, 0, by the column stride, add them all up, and bam, that's the exact location in memory. It's a simple formula that turns our logical idea into a physical address. Okay, that's a neat trick, but why does it matter so much? What's the big payoff? Well, this whole clever system of strides is what unlocks one of PyTorch's most powerful and efficient features, memory views. Let's see it in action. This is so important. Let's compare taking a view of a tensor versus making a copy. When you ask for a slice, like tensor1 square, PyTorch doesn't have to create a whole new tensor from scratch. It just creates a new, tiny tensor object with different strides that points to the exact same memory as the original. It is instantaneous. A copy with .clone has to actually allocate brand new memory and duplicate all the data. That is a massive, massive performance win, and it is all thanks to strides. So this really formalizes the key separation inside PyTorch. You have the storage, which is that actual physical block of memory. Then you have the tensor, which is just the logical interpretation. It's the lens, the set of rules with sizes and strides that tells us how to read that memory. And that's exactly why you can have many different tensors or views, all sharing one single storage. Okay, so we've got the data structure down, but what happens when we actually do something with it, like when we call torch.add? Well, now we're heading into the engine room to talk about something called dispatch. Think of dispatch like a really smart two-step routing system. The first step is the device and layout dispatch. PyTorch looks at your tensor and asks, okay, is this on the CPU or a CUDA GPU? Is it a normal tensor or something weird like a sparse tensor? This is a dynamic call that sends the operation to the right high-level library. Then, once it's in the right place, the second step happens, the data type dispatch. This is just a simple switch statement that says, all right, are we working with floats or ints or half-precision floats? And it funnels the operation to the exact super-optimized piece of code for that specific data type. Now, if tensors and fast operations were all PyTorch had, it would basically just be a NumPy clone on steroids. But the feature that turned it into a deep learning juggernaut, its real magic trick, is automatic differentiation, or as we all know it, autograd. And
Honestly, that's not an exaggeration at all. Autograd is the engine that lets us train neural networks. It is the absolute game changer that transforms PyTorch from a simple tensor library into a powerhouse for deep learning, because it automatically calculates all the gradients we could ever need.
So how does it pull this off? Well, at its core, PyTorch uses something called reverse mode automatic differentiation. Basically, as your code runs forward making predictions, PyTorch is quietly in the background, building up a graph of every single operation you perform. Then, when you call dot backward, it just walks that graph in reverse, applying the chain rule at every single step to calculate all the gradients super efficiently. So, under the hood, how is this implemented? Well, nowadays, all that autograd metadata is attached directly to the tensor object itself. If you've been using PyTorch for a while, you might remember the old variable class that used to wrap tensors. It's the same idea, just integrated more tightly now. And this actually adds a whole new layer of dispatch that happens even before the device and data type dispatch we just talked about. It intercepts the call, records the operation for the backward pass, and then passes it along. Whew, okay, we have the core concepts down. We've got tensors, we've got strides, dispatch, and autograd. Now, as promised at the very beginning, here is your map to the actual C++ codebase, so you know exactly where to find these big ideas in the source code. Honestly, there are really just 4 directories you need to know to get started. Torch slash, that's all the Python stuff you're used to importing. Then torch slash csrc, that's the C++ front end, the glue that binds Python to C++, and it's also where the autograd engine lives. Then there's aten slash, which stands for a tensor library. This is where the actual C++ implementations of operations like add and multiply are. And finally, c10 slash, which is short for cafe 10, contains the most fundamental building blocks, like the C++ definitions for tensor and storage. And this brings us to a really, really important point, and it's summed up perfectly in this quote from Ed Young, the author of the blog post this is based on. The strength of PyTorch comes from its community. Understanding all this internal stuff isn't just some academic exercise. It's really an invitation to get involved and contribute. So look at that. We've gone all the way from the simple logical idea of a tensor down through its physical memory, through the dispatch system, through autograd, and landed on the exact directories in the C++ source code. The codebase isn't some scary monolith anymore. It's a landscape, and now you have the landmarks. So I'll just leave you with this final thought. Now that you have the map, where are you going to start exploring?